Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 4, probability. For probability, there are plenty of things we need to cover. In the previous sections, I believe we took a look at how we learned how to find probability that two events occurs in sequence. Not in sequence. I'm sorry. So we find how to determine probabilities when you know the total and also when you know the frequency. And we learn about sample space event, simple event in generals, so we talked about it. And we know what to do when it's significantly high, if it's significantly low, or it's neither. In this section, so we're going really to take a look on how to find probability that two events occurred in sequence. Yeah, that's very important. But before we can do that, we need to learn how to find probabilities when we deal with conditional. So that's mostly what we're gonna do. That's additional rules and multiplication rules. So in this case, we're gonna do a lot of computations of probabilities. The key of this, if I review very quick what we've covered in terms of not really what we covered, what the topics will be for this section. So we will develop the ability to calculate probability that in a single trial, some event A occurs, or remember the conjunction, or some event B occurs, or they both occur at the same time. So apply the addition rule by correctly adjusting for events that are not disjoint. We're going to talk about these events that are disjoint or they are overlapping. We would develop the ability to calculate the probability of an event A occurring in a first trial and an event B occurring in a second trial. So we're going to apply the multiplication rule by adjusting for events that are not independent. We will distinguish between independent events and dependent events. That's mostly what we're planning on doing on these sessions. Let's start very quick by reviewing the key concepts that you would probably see in the book. We said we would present the addition rule as a tool for finding probability of A or B. In some books, a probability of A or B can also be written as probability of A union B. So if you see it that way, don't be surprised. So it's the probability that either event A occurs or event B occurs, or they both occurs at the same time as the single outcome of a procedure. The word or, which is a conjunction in the addition rule, is associated with the addition of probabilities. So this section also presents the basic multiplication rule using for finding probability of A and B. If you see probability A and B, or if you see probability of A intersect B, no, they are the same. Well, remember that symbols here I use is intersection, right? Intersection. I just use something you probably see before. That symbol is union. We'll probably have a chance to talk about it further. So what we mean by that, you see these two compound events. So our goal here is mostly to talk about compound events. So a compound event, because in the previous section, so we consider only simple events. But in this section, we would consider compound event. That is an event combining two or more simple events. Let's see for addition rule, of course. Probability notation for addition rule, probability of A or B, all right? Like probability of in a single trial event occur, or event B occurs, or they both occurs at the same time. So the word or used in the preceding notation is the inclusive or, which means either one of or the other or both would be included, right? So the formula addition rule is often presented as a formula, but blind use of formulas is not recommended, you know. So we really need, don't like close your eyes and use formula. You need to really understand the spirit of the rule and use the that understanding as the intuitive addition rule that follows. Of course, you know, because we have some special addition rule also, it's all depends that we're gonna have a chance to talk about. So to find probability of A or B, add the number of ways even A can occur, and then the number of ways even B can occur, but add in such a way that every outcome is counted once. So probability of A or B equal to the sum, to that sum, divided by the total number of outcome in the sample space. Most of all, what we mean, this is what happened. Let's see, for examples, we have let's suppose we have a sample space that we're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9. Or you know what? Let's put 0. I'm gonna include 0. The 10 digits, right? Okay. Now we have this. I have an even A. Let's put even A is a number less than 5. A number less than 5, or is a number between 1 and 7. A number between 1 and 7 is 2, 3, 4, 5, 6. Okay. Um, Now even B, let's do even B. What we're gonna do? Maybe even B is a number, okay, is an even number, is an odd number. 1, 3, I mean odd number, 1, 3, 5, 7, if you're okay with that, right? Now we can even include in events C. Let's put an event C. C, for example, all right? We can have event C, okay? What number we can include is a number greater than 6. A number greater than 6 is 7, 8, and 9. We're gonna have this. Now, I'm going just to move it just for you to see because we're gonna use that examples. The first thing we can do for this example is to use something we call a Venn diagram to represent our event. So first of all, you know, to construct a Venn diagram, you know, a Venn diagram, you need to have a rectangle and you have some circle represent that would probably overlap. So I can make them all overlap like I have A, I have B, and I have C. Now, in this one, we can say, oh, what are the elements you find in all three? Elements you find in all three would probably be here, but because we don't have elements you find in all three, because the C has 7, B has 7, but A doesn't have 7, we can erase it. So in this case, we're gonna just do, we see, I mean, I can do either two together. Let's do A and B. A and B has, what do they have in common? A and B, A and B has 3 and 5, right? 3 and 5. So we're gonna do A and B have 3, 5. Now, A and C has nothing in common, but B and C has 7 in common. So for B, for C, what we have left is only 8 and 9 because you know what? B has one more that I didn't include because we said they are all even numbers, odd numbers, 1, 3, 5, 7, 9. Let's put it that way. So in this case, let me go back to my green. We said 7 and 9 would be in these two. 7, 9. So the only thing that is only on C is 8. Okay. Now we're done with C. How about we already know B? 1 is only in B. And that's it. That's the only one because now you count 1, 3, 5, 7, 9. Now A already has 3, 5. Okay. 2 would be here. That's the only place you can find 2. 4 is here. The only place you can find 4. And 6 is also here. So the only number that is not in none of them, we put it outside, is 0. So we call this one a Venn diagram. Now let's see. If they ask you what is the probability of A or B? Probability of A or B is probability of A plus probability of B minus probability of A and B. What do you find in A? You also, now remember, you find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so probability of A would be, the number of data you see in A, which is 5 out of 10, plus probability of B is 1, 2, 3, 4, 5 out of 10, minus whatever they have in common. What do these two have in common? 3 and 5, 2 digits, so 2 over 10. So you see 10, that would be 8 over 10, that's you simplify by 2, that's 4/5. So that would be the probability of A or B. But if they ask you what is the probability of A or C, remember A or C would be probability of A plus probability of C plus probability of A and C. Now look, for A, probability of A, we know it's 5 over 10. How many elements in C? 3. 3 out plus 3 out of 10. Now, how about how many you see in A? You also see it in C. Well, I put plus, that should be minus. Sorry about that. That's minus. Okay, so there is none. So that's why we call this one a special addition rule, and it will still give you 8 over 10, so 4 over 5. That's a probability as well. But you see, we don't subtract anything because there is nothing in common between these. So that's why we said you need to make sure you really need to understand the spirit of the rule and use that understanding as in the instruction addition rule that okay, so that's very important. We said disjoint. Now let's suppose we toss a die. If you toss a die, right, and the sample space is 1, 2, 3, 4, 5, and 6. If you toss a die there are 6 possible outcomes. And if you have an event A, you toss a even number, 2, 4, and 6. Those are even numbers. And B, you toss an odd number, 1, 3, 5. So now, if you want to represent these two events in a Venn diagram, look at these two events. They have nothing in common. So event A and event B, because one has all the even number and the other one has all the odd numbers. So they have nothing in common. We call that disjoint or mutually exclusive events. Even A and B are disjoint or mutually exclusive if they have nothing in common. I mean, if they cannot occur at the same time, that is, disjoint events do not overlap. So you see, for this one, they don't have any intersection like the first one. You see, the first one, A intersect B. There is something between A and B, but here there is nothing. Disjoint events, so like randomly select someone for a clinical trial who is male, randomly select someone for a clinical trial who is female, so they cannot be both. Of course, but I understand how sensitive that can be for now. But let's suppose we're talking about being male and female at the same times. It's not currently something you can see. So that disjoint. However, look at when it's not disjoint. Randomly selecting someone taking statistic course and randomly select a female. So they are not disjoint because someone who is taking a statistic course can also be female. So that's not disjoint. Disjoint is when they have nothing in common. Summary, here's a summary of the key points of the addition rule so far to find probability of A or B. Remember the or, very important. We said probability of A or B is probability of A plus probability of B minus probability of A and B. But if for disjoint events, probability of A or B would simply be probability of A plus probability of B. We can say for disjoint. When they have nothing in common, the last part is zero. Okay? So the first one is possible for a special addition rule. To find the value of probability of A or B, as we said, we add the number of ways A can occur and the number of ways B can occur. But we be careful without doubling. I mean, we need to avoid anything that has to do with overlap. So complementary events and the addition. Well, we talked about this one already. We use not A, that the A bar. When you see this one, we call it not A. That means to indicate that even it does not occur. Common sense dictates this principle. We are certain with probability 100% that either an event A occurs or it does not occur. So it follows that probability of A or B, is that probability of A plus probability of not A equal 100%. Probability that something happened plus probability something does not happen is 100%, right? Because even A and not A must be disjoint, right? So we can use the addition rule to express this like that. So what we see here, remember we said if you know the probability something happen, you can subtract it from 1. If you know the probability something cannot happen, you subtract it from 1 to find the probability it's happened. Let's go with our first examples. In a very simple examples here, they said find the indicative complements there, as I said. In a recent year, speaking characters in movies were 68.2% male. So if you want, you can rewrite it as 0.682. That's fine too in decimal. What is the probability of randomly selecting a character with speaking part and getting a female? Assume we have only two categories, male and females. So all you need to do to find part A is subtract the whole probabilities from 100%. So in order to do that, you're going to find 0.318. So the probability, they said, what should be the value of that probability? That's what we find, okay? So I think we get it, right? Okay. The probability should be like you know 33 point something, all right? It's probably like because in a recently speaking characters in so what is the probability of selecting a character with a speaking part and getting a female? Only 31 point, you can rewrite it 31.8%. So what should the value of the probability be like? Like 50%. It must be 50-50. In a new world, there should be 50% of it. Based on a survey by Consumer Technology Association, smartwatches are used in 18% of households. 18% of households use smartwatches. So, what's the probability that a randomly select US household has no smartwatches? So, what would that be? Yes, because remember 18% is like 0.18. So if you do 1 minus 0.18, what do you have left? 0.82, that you can write 82%. For C, based on a new generation of STAN survey, 13% of US adults know that the care instruction symbol delta, that's on clothing means that any bleach can be used. Only 18% knows that. So what is the probability of randomly selecting an adult in the US who doesn't know it? So 13% know it, like it's 0.13. So how many doesn't know it? Yeah, you need to subtract it from 100%. So 0.87%, or 87% people doesn't know it. So we call this complement rules. All right. We're gonna have a chance to go back and do more on, to start doing some on the addition rules. Before we do addition rules, let's review very quick about multiplication rules. Because addition rules, as we said, is important. All right. But multiplication rules is something different. So, we said two events are independent, yeah, I mean multiplication. To find the probability of two events occurring in sequence, you can use the multiplication rule. Probability of A and B, probability A occurs in the first trial, and event B occurs in the second trial. That means they happen in sequence. Or we can write it, probability of P slash, probability of B given A. Let's go on. Probability of B given A. Right? So represent the probability of event B occurring after it is assumed that event A has already occurred. So that's what we do. If events A and B are, we have two events, we said it's occurrence of A and B, right? So that's very important to see in this case. So to find the probability of that event A occurs in one trial and event B occurs in another trial, multiply the probability of it A and B. So if you find probability of A uh, and B, you can do probability of A times probability of B, right? But we don't quite write it like this because in order to find probability of A and B, we said that we multiply A and B. First of all, you need to make sure that in order to find probability of A, we need to make sure that we find probability of B given that you already do A. Because you do A, then you do B because you already do A. That's how we're gonna write it. Be sure to probability of an event A is found by assuming event A has already occurred. That's why we need to write it that way. This is how we write it. Okay. Probability events A and B, we can write it like this. Okay. The probability that two events probability that two events A and B, okay, will occur in sequence, right? So that's how we write it, right? Probability of A and B, okay, equal probability of A times, that's how we do, remember you do probability of A and B equal probability of A times probability of B given A. So you cannot multiply them if you're not certain that A already occurs. So, all right. Now, independency and the multiplication. Well, independent. Two events A and B are independent if the occurrence of one does not affect the other ones, right? So, for example, if you toss a coin and obtain a head, and you flip a die and you obtain a five, you see, obtaining a head has no impact. Obtaining a head from flipping a coin has no impact when you tossing a die, you obtain a five. So they don't have any effects on it. So they are totally independent events. So the occurrence of one does not affect the probability of occurrence of the other one. So several events are independent if the occurrence of any does not affect the probabilities of the occurrence of the other ones, right? So that's very important to see. Even in a playing card, if you try to obtain a king, then you obtain a 10. As long as you do it with replacement, one doesn't affect the other one. If A and B are not independent, we call it dependent, right? Dependent. That's also something. Let's see through an examples very quick because we have so many examples. Like when we say dependent, let's say you drive you drive over 90 miles per hour on the highway. That whose speed limit is only 65, and you get a ticket. Yes, these two events are dependent. The only reason you get a ticket is because you do over the speed limit. So that's dependent. Okay. But if you flip a coin, and you toss a die, the result one doesn't affect the other one. Let's see what we're gonna do with these examples because for this one we're going to use both addition and I don't know how many rows we're gonna do. But the first thing, these tables, as you can see, we call it, you didn't know it, but it's a tables. We call this type of table contingency tables. What I'm going to do is reduce this to 15 so we have more space and we can put this one up a little bit. I'm going to reduce ABC to 15 also, hoping you can read it, and I'll put it down. Because anytime you have a table like this, the first thing to do is to find the row total. You need to add another row for the total. I didn't do it because I want you to pay attention to it. It's extremely important. This line is terribly terrible, right? Let's redo it. Yeah, I do better. Now we need to do a colon total. In some exercise, this already given, but for you, you add. Let's say colon totals. I know this one is the same. I don't need it. This one I don't need. I only need to do totals here. Right? What happened? You add 731 to 54. If you add these two, it gives you 37. 85. In some tables, they're already given, but if you do 156 plus 45, 64, 47, 20. Now, if you do the colon total now, because I'm done with row, let's do the colon. So 731 plus 156 is 8. 87. 3054 plus 4564 is 76, 18. Now, either when you add the colon totals or the row totals, the big totals must be the same. So it would be 85 5. So always verify and make sure the answer is always correct because I did it using my calculator, my beautiful TI-89. So you can always check and make sure the answer is really 8505 in both ways. Either you add 3785 plus 4720. Yes, 85 or 5 in both ways. So we're done with the tables. We call this table is called contingency table. Contingency table, right? It's called contingency table. This is a beautiful tables. You must have total rows and total columns in it. Okay. So now we can answer any of these questions asked. The first questions they ask us to do, if one of the highway, you know what? What about we put in letter for this because it's gonna make it much easier for us. I'm gonna call this one A. So when I do probability of A, probability of B. So no text. Okay. How about we do no text while driving is probability of A, and text while I mean B, text while driving is probability of B. We're gonna use Y for this one, and we're gonna use N for the one to make it shorter. If one of the high school drivers is randomly selected, find the probability of getting one who drove when drinking alcohol. So drove when drinking alcohol, yes. What is it? We're gonna say probability that drinking alcohol. All right. Yes. What is the probability? First of all, you need to find the total for both drink. We focus only on drinking alcohol. How many drinking alcohol in total? Yes. 887. Okay. So that would be 887 over the big total, which is 8505. Now you can simplify into decimal. That gives you 0.104. Now, for B, find the probability of getting one who text, did not text while driving is probability of B. I call it B. Did not text while driving. Did not text. What is the total for did not text while driving? Yes, 4720 over 8505. Express it in decimal 0.555. All right. Now, you see, the totals are very important. We take the whole total. We don't focus inside of the cells, right? I mean, the one in the middle, the one is given yet. If one of the high school drivers is randomly select, find the probability of getting one who texts while driving or text while driving or drove when drinking alcohol. What are the letters? Probability that you text while driving, we call it A, or what again? Or drove when drinking alcohol. So that's yes. So remember that formula? Probability of A or B. Remember we said probability of A or B is probability of A plus probability of B minus probability of A and B. So we said that before. We can reproduce it here. It's probability of A plus probability of Y, which is drinking alcohol, minus the intersection between these two. Okay? All right, I'm gonna try to put this one a little bit down so I have enough space for it. Okay, let's try it. That's a lot. Maybe I have enough space for the other one too. Let's try that. Okay, that's all I need. Okay, probability of A or Y, that's always zero. What is the probability that one who texts while driving. Text while driving, you see that big number is 3785 over the big total, 8505, plus probability drove when drinking alcohol is 887 over 8505 minus the intersection of these two. What is the intersection of text while driving and uh, drink alcohol? This is it. That's the intersection. So we need to remove anything that would overlap. So we take 731 over 85. Now, when you subtract and simplify, you're going to find 3941 over 8505. Answer would be 0.463. 0.463. Okay. So when we see that 0.463, that would be the probability, the two events. Do you feel like they are disjoint or not disjoint? Because they're gonna ask you, because we can subtract probability of A and Y, that means they are not disjoint. So these two are not disjoint. Now let's see for the last one, if one of the high school drivers is randomly select, find the probability of getting one who did not text while driving. Or again, we're doing a beautiful all means remember all means union. We need to rewrite it. Okay, who did not text, so we're gonna say probability of B, or drove when drinking alcohol. Okay, drove when drinking alcohol. We said drove when drinking alcohol is another yes, right? We're gonna do the same thing, like, oh, that's probability of B plus probability of Y minus probability of B and Y. Remember, I simply do it to make it shorter to write AB. So if you want to write the whole thing text while driving or no text while you feel free to do that. So probability of B, the whole thing is 4720, where the big total 8505 plus drinking alcohol is 887 over the big total 8505. Now you need to look for where it is, both of them, who did not text while driving and drinking alcohol is that number 156. We need to remove it because we need to avoid redundancy, right? So 8505. When you simplify, remember, same denominator, you add and subtract the numerators, you'll find 5451 over 8505, and expressed into decimal is 0.641. Again, they are not disjoint. The reason they are not disjoint is because you have the parts of probability of A and B. A and B. That's very, very important. Now, before we move any further, we're gonna review about sampling. Sampling, remember, it's really simple. We need to do some sampling, very important. In the world of statistics, in the world of statistics, we can say that sampling methods are critically important, and the following relationships hold. Sampling with replacement, selections are independent events. With replacement, that means, you in a standard deck of 52 playing cards, you select a king with replacement, and you select another king, or you can select, a red card. All right. So with replacement is very important. And when you do it without replacement, selections are dependent. So when you don't replace, it's independent. When you replace, it's independent. When you don't replace, it's independent. Because look, probability you select a king in a standard deck is for over 52 because there are 52 playing cards. Probability you select a queen, even king and queen are different. You're gonna select now because you replace it, you select it again over 52. But look at down here. If you select, first of all, you select a king, you select it out of 52 card. But if you don't replace it, when you select your queen, you would select it out of 51, which would be different. So that's very important to pay attention to this. Treating independent events and independent events, 5% guidelines for cumbersome calculations when sampling without replacement and the sample size is no more than 5% of the size of the population. Treat this selection as being independent. So that's simple. Let's see a few examples very quick. Use the data in the following table, which lists survey results from high school drivers at least. Oh, we did that one. No, let's just, I'm gonna just come back. I'm gonna put this one down here and I'm going to remove this and probably because copying, I'm not going to do the additions anymore. I'll do it once. Let's take this one right here. I copy. I go back here and I place it. Yeah, I make less work. Okay, so if you're okay with that, I'm okay with it. Okay, all right. I'm going just to remove the yellow. All right, let's see it. Because it's exactly the same exercise. The same exercise, the only difference. uh, Okay, let's see it. What? No. Okay. If two of the high school drivers are randomly selected, because we're using the same tables, the same contingency tables, we'll do number 4, 5, I believe 4, 5, 6. Okay. 3, 4, 5, 6. We're gonna do the same. Um, Two of the high school drivers are randomly selected. Now, when we do two in sequence, we're dealing with multiplication rule. Find the probability that they both drive when drinking alcohol. In the first one, what we need to remember in the first one is that, oh, they said do it with replacements. That means, okay, find the probability both drank when doing alcohol. So both drink when drinking alcohol. That means you're gonna have 7 over the total 8505. All right. Now, what we need to do in this case, remember the next one, because this is both drinks when drinking alcohol. Now, the second one, because you do replacement, you're gonna take the second one also. They happen in sequence, but you're gonna use it like this. Okay, you multiply these two, you know, probabilities. If you simplify, it gives you 0.0109. Sorry. So these events are really independent because you do it with replacement, there is no problem. But look at the second one. Yes, independent. Now look at the second one. I'll try. The second one, you do it without replacement. Without replacement. That means when you do it without replacement, you take the first one who drive when drinking alcohol. Now the second one, because if you remove one, You no longer have 887 because you don't replace it. You have 886 over what again? Yeah, because you need to remove it also in the denominator. 85, 84, 8504. So when you multiply these two probabilities, or you find each probability separately, you multiply them, or you multiply the numerators together and multiply the denominators together, right? Then the answer would be very close to it. I think, if you take only 4 decimal point, yes, this event also, no, this event is not, I was almost say it's, no, the event is not independent. It's dependent, not independent. It's dependent. Why it's dependent? Because we do it without replacement. You see, the second one, we find it differently. Are these preceding results the same? Well, actually, they result the same, but if you take more digits, it would probably be different, okay? It would probably be different. Now, let's see for a different examples. Now, we said find the probability that both drove when drinking alcohol. Now, if you do find the probability that they both text while driving, I think you believe like text while driving for both of them, while text while driving, remember you take this one over the total. Again, here I would leave this one for you, but I'm gonna go with the next one because every time I do one, I'm just checking. Okay, this one would probably be different. Let's do this one. Again, my plan. Okay, so my plan in this case is the same. I want to be lazy. I would remove these tables and I would replace it with what I did before, right? Very important. That's quite amazing and important. All right, let's do it. Then I remove this one down there because I feel like it's the same. Now, those are the two questions asked. They said, if three of the high school, we have the three of the high school. Now, if three of the high school, three of the high school drivers are randomly select from the 4,720 subject who did not text while driving, because that's the number we're gonna take. Okay. Now we said, well, driving find the probability that all three drove when drinking. All three. All three drove when drinking. Now we do it out of, because they said do it out of 4720. All three while drinking, text while all three drove while drinking. Okay, so what number would that be? Yes, 156 times. Now assume that the selection I made with replacement. So 156 again over the same number, 4720, times 156 again over 4720. Now, when you multiply these three, answer would probably be like 0. When I did it, how many zeros did I find? I believe it was 4 zeros. 1, 2, 3, 4, 361. So again, yes. Now, for the second one, they said without replacement. Remember, without replacement, all three 156 out of the 4720 times. Would we take 156 again? No, we're gonna go 155 because we didn't replace the first one we take out of what? 4719. You do good. And 150, yes, 54 out of 4718. Find, multiply all the numerators together and all the denominators together and divide, or you can divide each fraction separately. And at the end, you multiply, it's 0. you find four zeros, 1, 2, 3, and 4, 3, 5, 4. No, the events not no, it's not independence because you do it without replacement. So it's mostly dependence. Okay. So I left the number 4 for you. I believe that would be the same here. If doing the same thing here, we're gonna ask you those questions. Oh, maybe that will be different. Now let's see if I remove that one and try to get this one even smaller. Let's do 14 because you already see what we're talking about. Okay. Um, remove that yellow. Oops, that's not what we're doing. Are we? Hey, let's put this one also 14. We need space. Okay, I'm pretty sure we're gonna have enough space for some of them, because we're gonna do it very quick. These examples, they said use the same data. If one of the high school drivers is randomly select, find the probability that the selected driver text while driving and drove when drinking alcohol. So for now, what you need to see here, you drive and remember the and is look for the number for both of them. So that would be probably 731 over what? Because we only focus on and. Yes, that would be 8505. So and given that, okay. So we said 7 okay, 731. So if one of the high school drivers is randomly selected, find the probability that the selected driver texts while driving and drinking alcohol. So you can do this and find the probabilities to be 0.0859. Let's go with the second one. Find the probability that they all drove when drinking alcohol. You said no, number BB. If one of the high school drivers is randomly select one, find the probability that the select driver did not drink alcohol and did not drive when drinking alcohol. Okay? Did not text, did not drink. So did not text, did not drink. The answer would be that big 47. That's the number here. Did not drink, and it's willing. As I said, this is this number. Okay. So it would give us 4564 over 8505. So 8505. So remember, that's what's gonna happen with this right now. Okay. So we're gonna we need to a calculator. The calculator would give us this beautiful answer of 0.537. Now let's go for 4. With 4, we said if four if four different high school drivers are randomly selected, so randomly selected, not a randomly, is randomly selected. Find a probability that they all drive when drinking alcohols. Okay, they don't say replacement, they don't say without replacement, but we're gonna go without replacement. So remember, uh, find the probability that they all drink alcohol. So we do 887 drinking alcohol over 8505. 85. Now we no longer 85, 86, but 87 is 86 because we already used the first one, and we're gonna have four of them, right? That's 48503, okay, times 8848502. So when you multiply each of these probabilities, you obtain 0.0000118. Now, we said I leave the last one for you. As always, you see it's similar to C. Very important. Now, let's do something very simple about redundancy, because that's something else we need to address very quick. We said that the principle of redundancy is used to increase the reliability of many systems. Our eyes have perceived redundancy in the sense that if one of them fails, we continue to see. An important finding of modern biology is that genes in organisms can often work in place of each other. Engineers often design redundant components so that the whole system will not fail because of the failure of a single component. So we do redundancy, but let's see for these examples. It's very simple as well to see. Each of us must sometimes wake up early for something really important, such as final exam, job interview, or early flight. Professional golfer Jim Furyk was disqualified from a tournament when his cell phone lost battery and he overslept. And it's happened for too many people. Assume that a battery powered alarm clock has a 0.005 probability of a failure. So we have three of them. Battery power clock. And we have a smart alarm clock. And we have an electric alarm clock. So three of them. We said, each of them has a number, has their own failures. What is the probability? That's something you need to verify when we ask you for it. What is the probability that your single battery powered alarm clock works successfully when you need it? I mean, we're going with the battery. That's the one that we go for. The battery power clock. So if it fails 0.05 or 0.5%, when do you think it succeed? Yes, you need to subtract it from 1 and you would find when it succeed. So it's really succeed at really 0.995, or you can say 99.5% at the time. So it's really accurate. If you use a battery powered alarm clock and a smartphone alarm clock, what is the probability that they both fail doing multiplications? Remember, it's happening in sequence. So battery power alarm clock fell 0.005 times probability, and if it's a smartphone, it's fell 0.052. So when you multiply these two together, based on what I have, it's 0. I think it's 30260. Now they ask you, that's the answer. What is the probability that both of them do not fail? So if both of them do not fail, just subtract what you got from 100, and it would give you like 0 point, a lot of nines, maybe 697, 1, 2, 3, 4, 5, 6, 7, 4. All right. If you use a battery alarm clock and a smartphone alarm clock and an electric alarm clock, they do all three at the same times, and ask you what is the probability that all fail, just multiply all three. 0.005 times 0.052 times 0.001. Remember, they happen in sequence. Now, doing this like that, I'm pretty sure we're gonna find a big number that we cannot even read, which is, um, I believe it's 6 zeros in my calculator. 1, 2, 3, 4, 5, 6, 26. That is the answer when you multiply all three. The same thing, if they ask you what is the probability that they express both of these answers using either 8 decimal, I believe that's 8 decimals, we do, right? Not sure the answers. So my answer for the second one, what's the probability you don't fail? So that was the correct answer for because those are different. Sorry, I messed up my two answers. The first one would give you only 3 9s. 1, 2, 3, 7, 4. But the second one, when you subtract the 6 zeros, it would give you 0.96 times 7 4 when you succeed when it is successful. Now they said what configuration gives you the best chance to wake up for sometimes really important. I think you need to combine these three because you need to find a way to have all three works together very well. Addition rule as a summary, very important. The word also just addition when adding probability of A and B. We must add in certain way the counts only once. We need to avoid overlap. Multiplication rule for A and B, the word and for to trial suggests multiplication, and when multiplying A and B, we must be sure that the probability of A, even B, takes into account the previous occurrence of event A. Hope that's helped. I'll see you in a different video for section 4.3 complement conditional probabilities and Bayes theorem. Take care. Have a good day.